Hey everyone, I'm Nick from Coffee Before Arch, and in this video of systems programming, we're going to continue on with this our discussion on file I/O, and we're going to actually do something with these files that we've learned about opening and closing and creating new files. And that's of course the basic operation of reading from files. So we're going to go ahead and build on this idea of opening files that we looked at in the first video with read, and we're going to include a lot of headers that we've seen before and a couple new ones. Some of which aren't necessarily specific to systems programming. So of course we need the file control so we can open files. We'll go ahead and need the standard file for reading and closing, and we'll go ahead and include this error number file, and this is what we'll use to check return codes for when a system call fails. So when a system call fails, there's actually another variable that ends up getting updated that we can check. And not every single time that a system call fails doesn't mean we need to kill a program. Sometimes it's a recoverable error. We can just reissue the system call. So we'll use this error number variable for that. Then we'll include the standard library, this standard lib.h. We'll use that for some memory allocation, stdio.h for some printing, and of course assert.h for some checking and for killing the program if we run into something that's non-recoverable. So what we'll go ahead and start doing is opening our file, and we'll open it in read-only mode. And this test.txt is a file from the first example. So we'll go ahead and open test.txt, and all it says is this is a sample file. Now going back to our program, of course, when we're reading something in, we've got to have a space for whatever we read in. So in this case, we'll create a 100 element buffer of characters. So we'll have a character pointer called buffer, and then that pointer will point to, we'll use calloc, which is for 0 allocation. So we allocate some size memory and it'll be 0 allocated, or rather it will be allocated and initialized to 0. And so we'll do 100 elements of characters, and then we'll go ahead and cast it to a character pointer, right? And so we'll basically have 100 bytes to store things in. Now, as far as our return value from read, so what the read system call actually returns is going to be the amount of bytes that that were read by that system call. And there's 3 different scenarios we have to keep track of. We have to keep track of if read returns -1, that means the system call failed, and we'll go ahead and check that error number variable to see why it failed. Another thing that could happen is it could return 0, and that just means that it ran out of things to read. So that just means that our file is now empty, or rather we've hit kind of like the end of file. Then the next thing that we have is if it's a positive number, right? So if it's 1 or greater, up to the max length of read. So in that case, that will just be how many bytes were actually read in that system call. So if we wanted to read an entire file, we do something like this. So the first condition we check is if length is not equal to 0. Now length is the size of our buffer, so we'll keep track of how much of the buffer we've used. So as long as our buffer length is not 0, we'll keep reading. And then the other condition that we need to have, so we'll go ahead and AND it with whatever the return value is not equal to 0. So if the return value is equal to 0, like I said, that means we've hit kind of the end of file, so we're done reading. Now as far as the read system call goes itself, it requires a file descriptor, so where it's going to be reading from. It'll need some place to read in the contents into. So in this case, buffer is our pointer, and we'll go ahead and offset it by some position. So we want to make sure that we're not overwriting the data we already read in, so we need to move that, we need to do some pointer arithmetic and add to that pointer to make sure that it's pointing to a byte that hasn't been used yet. And so we start the position at 0, so we'll initially be pointing to the first element in that array, but as you read in bytes, we'll be pointing to later and later elements. And then of course, how many bytes we're reading. So in this case, we're reading in length bytes, so this is just saying I've got a buffer of 100 bytes. I want you to read 100 of them in. However, this doesn't we can say we want to read in more bytes than actually exist. What will end up happening is we'll read in some amount of bytes, and then we'll end up getting a 0 as a return from read the next time around. Right, so just to briefly summarize it, we check to make sure we have buffer space, and we check to make sure we're not at the end of the file. So if we're at the end of the file or we're out of buffer space, we'll go ahead and just exit the while loop. Now, if we've read something in or there was a problem, we'll go into the while loop. Now, if we get a -1, that means there was a problem. We don't have to die right away or kill the program right away. We can go ahead and check the automatically updated error number variable. And this is, of course, really only valid to check if there's an error with the system call, which is why we only check it if the return value is -1. Now, in this case, we'll go ahead and check the specific flag, and this flag says that a signal was received before any bytes were read. Now, this is important to us because it means that it's safe to reissue this. This just means that we haven't done anything. We're not in some weird intermediate state. This is something that we can recover from. No bytes that we were trying to read were actually read, so go ahead and just reissue read. So we'll go ahead and continue here, so we skip over kind of the state updating we do later on in this while loop. Otherwise, we'll just assume everything else is a non-recoverable error, and we'll go ahead and just assert 0. Now, if we want to do non-blocking I/O, where we're not waiting for successful completion right away, we would have to open the file in a little bit of a different manner, and we'd also have to handle another type of error number in here. But that'll be something that we either cover in a later video, or if that's something that people are interested in. So moving on to the successful case, so when we actually read bytes in, what we'll end up doing is we'll decrease length. So this just means that we're decreasing the amount of buffer space that we're keeping track of. So if we have a length is equal to 100 and we read in 20 bytes, well, length should reflect 80 bytes now because we really only have 80 bytes left over. Then we'll go ahead and move the position over by how many we read. So if we've filled bytes 0 through 19, right? So if we've read 20 bytes, we want to make sure the pointer is pointing to byte 20, right? Because 0 and 19 are now filled. And then down here, we'll go ahead and print out how many bytes we read, what the updated length is, and the updated position. And so right here is the end of the, this is going to be the end of the while loop right here. So if we're into the while loop, that means one of those conditions failed. So either the buffer ran out of space or the file ran out of contents. So we'll go ahead and close the file here with close, and we'll check to make sure that the close didn't fail. Then at the very end, we'll go ahead and print that read completed, and we'll print out the message we read. And the message is just stored in that buffer that we allocated earlier. Right, and remember what we're reading in, so we'll quit out of that. We're going to be reading in this test.txt. So let's go ahead and compile this. So we'll do gcc-o on read.c, and we'll go ahead and run read. So here we see that we read 23 bytes. We updated length to 77, so 100 minus 23, and our updated position is 23. So we've moved that pointer 23 bytes over. And then it says read completed, and it says message, this is a sample file, right? And so, in this case, we tried to read in 100 bytes, but our file only contained 23 bytes of data, so it exited early. Now, we can kind of predict this ahead of time if we just do ls-l on test.txt, and we can actually get the size of the file. So the size of the file is actually right there. It's just a coincidence that I happened to make this file on May 23rd, but this corresponds to the this will correspond to the size in bytes of the file. So if I do something like ls-la, it'll be for all the files, right? And you'll see that they're all kind of different sizes. And in this case, test.txt, which is what we read from, is 23 bytes. So it makes sense that the amount of bytes we read was 23, and that's the amount of bytes to store this message. This is a sample file. So that's going to go ahead for the basics of the read system call in Linux. As always, feel free to check out all the code that I post here at github.com/coffeebeforearch. We've got all kinds of stuff on C++, parallel programming, GPU programming with CUDA, and things like that. So we looked at systems programming. So if we go to repositories, we go to systems programming. The example we looked at today was under file IO. Oh, and it looks like I haven't committed it yet. So we can actually commit it. We'll commit it here together, right? So we'll go ahead and get rid of read, and we'll get rid of, I think that's it, right? We'll check the status. We'll add read. We'll do add read example, and then we'll go ahead and push it to the coffee before Arch. Uh-oh, I must have forgotten something. I didn't update the README. There we go. I had to merge that. All right, and so now we can push it successfully. There we go. So if we go ahead and reload this, we'll see that we've got read.c in here. So feel free to download this, play around with it. Let me know if you have any questions. And as always, I'm Nick from Coffee Before Arch, and I hope you have a nice day.